Hi, Martin. Would you like to start?
Sure, I can start. I just want to say I don't have much to present. I started yesterday, but I think I don't think I understand I have some misconceptions about how it's supposed to work. So I have just very little, but maybe people can help me out. And, can
Okay, yeah, we can try to figure out as we go along as a group whether what's going on. So let's go through as much as we can.
okay, yeah. So this is very limited. All I was trying to do was just understand this is from the collab. Just how do you fit the 1D continuous distribution, right? So that's all I want to start with, but I was completely confused about what's going on. So let me show so I copied over the code from the notebook to this file. So so when you run it, sorry, it shows you the this is the mixture of Gaussians that they start with, and then they create the data set from it, and then this is the final so the at each step of the training, these are the distribution that is changed to, right? So and then this is the training curve, so training loss and the test loss. So this part is the one that is using the uniform based distribution, right? So this is the one. So I can go over the code and then can try and like maybe someone with better understanding. It's the code is pretty much the same as before. So I think right. So we have the train part, which is exactly the same, the basic PyTorch. Every element in the training set, and then evaluate the loss, train epochs. All of these are the same, except that there's a plot after each epoch. Okay, so the main part is in this module, mixture CDF flow, and this function flow, right? So I was looking through it and I couldn't figure out what is going on. So okay, so I think that sort of the best way to think about to look at this is to say, okay, let's look at this plot. Plot will say, I can go to the lecture. So plot will say, here's X, and then what is the P theta of X? P is the probability distribution, theta is the parameters that we want to use, and then X is from the data, right? What is it that we want? So sort of go back from there, like how does everything work? So so obviously density, all it's doing is saying get the density, and then I'll plot the X and the Y of the density. So let's go to density. So here is just taking the plot bounds. This is one of the parameters. I think plot bounds is -3 to 3, right? Somewhere here, should be here. Plot bounds. I guess so. It's here somewhere. Jumping around here, -3 to 3. So when you calculate the density, you just say X is equally spaced 1,000 points over here, and then here's where we get the probability, this probability that we have, right? So all these probabilities. Okay, so then you take X and you say, give me the log probabilities of all of these values here, equally spaced. And then since it's a log probability, we'll exponentiate it, and then we'll just plot it. So like pretty straightforward, right? So, okay. So what exactly is log probability doing? And okay, so I changed this line to 2 lines here, but it's the same idea. So given X, you send it to flow, and it gives you the Z and log determinant back. And so this sort of is the place where it stops making sense for me. So okay, so what exactly is Z here, and what exactly is the log determinant? Because the distribution is now, so you can, this was the original line. The distribution is the base distribution log probability of Z plus the log determinant. So that is supposed to be the base distribution, the actual distribution. So here's the sort of the confusion. Let's look at flow then. So here's X, and all they're doing is they're repeating the X for the different Gaussians. So this is a mixture of Gaussians, right? Sorry, I don't know if I said it's a mixture of Gaussians. And if we look below, there's 5 of them, 5 mixture of 5 Gaussians there. So it's just repeating the X 5 times, and then Z is actually the mixture Gaussian. You take the CDF off it, and then multiply all of it, and then multiply it by the weights. Right. So the confusion here is that let's see. So here the diagram says we go through X and then goes through all of these, and then you get Z out. So, but here, I guess the notation is right. So here Z is actually F theta of X. So this would be the mixture of Gaussians. And so I'm not sure where the flow is going, which direction it's going, because as soon as you want the flow, you're just putting it directly here into F theta, which is the last part of it, but the flow points the other way. So yeah, I don't know. So I mean, this notation is right. So you're saying Z, they're saying is Z equals F theta of X. F theta is the mixture of Gaussians here. There's a mixture of 5 Gaussians, right?
Why do you say the flow points the other way? Because it is, taking in X and giving out Z and the determinant, yes, in the code.
But so it doesn't go through any of these boxes. It just goes through, X goes directly into F theta and gives you Z. So I don't know what these boxes are.
Maybe it's a single layer.
So there is 2 layers. So there's a base distribution, and then the mixer distribution, right? So there's 2 of them.
Okay.
So it's like,
isn't it the case that my recollection from the lecture, and again, any of my comments could be wrong, but I thought one of the things for the flow was to sample just from the uniform normal, but map it through the CDF of the distribution that we're trying, I think, to get at. And in this case, the CDF that we would want is the CDF of the mixture. But where we go, the source is kind of the data or the uniform normal or whatever. That's vaguely my recollection of the early part of the lecture, right? Because didn't he talk about mapping like from a sample X, but sampling from a uniform normal, which gives us, X, and then going to a different distribution, which is, and because we need to choose an invertible and CDF is an invertible function, then what we are after is these, or what we use the CDF for is the CDF of the mixture of Gaussian. Does that make sense in this context?
Yeah, I'm still not quite sure. So the other thing is like the base distribution is, uniform here, but it's not part of
Right.
the flow in any way.
But isn't, when you say not part of the flow, but
it's not used anywhere in the flow part. So all the
but where do you, so in the X is just the input in this particular case.
yeah. So you take
But
X.
sorry, if you go back to the code we were just beginning to look at, then isn't the output, if you look at the line that we wanted to look at the output of,
Yeah,
then
this one,
I'd be using self dot base distribution, and isn't that the base distribution is the the beta or the uniform?
yeah. So it seems like this is the only time it's used. So it's not really part of the flow, I guess.
Yeah. I think if you look at the flow function just slightly up, where it's got mixture distribution, so Z equals mixture distribution and your cumulative distribution function. So that mixture distribution there, that's your uniform.
Oh no, mixture is the
Mixture
Gaussian.
of Gaussians.
Yeah, normal.
Oh, sorry. Yeah, apologies for that.
Yeah,
I just confused myself. Yeah, apologies.
Yeah, I would think that there's a flow from uniform into normal, and it goes out. But the flow just takes it directly into the mixture, which is the I mean it makes sense from the diagram that f theta comes from X. But all of this stuff is not part of the flow. So
but let's keep going, assuming
okay.
that, as Sujit said, that this is just a single, instead of this multiple layer, in the simple case, it's just X going through the mixture distribution directly to Z, right? Because f theta is just a mixture of Gaussian.
Yeah. Okay. So let's assume that, like, if this was if we're not doing flows, we would just say, well, yeah, of course, fx, you just put it through here, and then you take the what is it called, the maximum likelihood, the log likelihood of this, and then you back propagate, right? So if it's just one layer, but so they do calculate the log determinant of it, right? So because it's a CDF, the determinant, the derivative is the PDF. And so they just say, give me the log probability of the X values. And then you exponentiate again, multiply by the weights, and then take the log again. So I don't know if this was necessary to do you could just do prop, but anyway, it's probably better for numerical. So they do calculate the log determinant and the Z value of both of these. So if we go here, somewhere, so calculate this log part of it, right? So you just take, since this is CDF, it becomes just the probability of each of the X's, and then you take the log of it. But since it's a mixture of Gauss,
and the first term, right? As well.
the first term isn't there yet.
Because the log determinant plus Z, right?
Oh, so Z is this term. So they did break it out. I think this is just this.
What I'm guessing. Can we go back to see whether that's my understanding?
So actually, f theta xi is Z. So I think we just get this part. This is, I can't highlight, this part is Z. F theta of xi is Z. And then they calculate the log of P of Z later on, I think. Yeah. So
I see. Okay.
so we have this part and this part, and then flow just gives you those parts. But it's just, I think it's just the end part of it. Maybe it's simplification because there's just one layer, but yeah. But then the base distribution, there's the uniform part isn't there, so it is used here.
Right.
Base distribution, log probabilities of Z.
Right. So in this case, what they seem to be doing is taking the log probability of Z, so converting, as you correctly pointed out, Z is f theta of x of I, so it's only the thing before the log in that equation, right? That from the slides.
Oh.
So we have to pause. So we have to kind of pass it into the log, which is why there is a log in the code. So if you go back to the code, then there, like you correctly pointed out, it's the log probability of Z. So that gets the log probability, and then that value is what you pass to the self dot base distribution, right? So you seem to be passing this first portion in and using the base distribution and passing in those values to sample from the base distribution to get to Z1.
Yeah. So this one is okay. I guess sort of makes sense. Like you're saying that we're calculating log p theta of xi, and then log p theta of xi would be log. Yeah, I don't know where Z would. Yeah, it's.
See, I think the
Okay.
and again, I'm also trying to understand as we go along, but assuming that the probability distribution of Z, the PZ, is a uniform normal, then what you do is you take the log of f theta of xi, which is, the log term, and then you pass that in through, now you want to sample from the base distribution, which is the uniform normal or the beta, using these values. So that's how you do the probability Z of f theta of xi, right? So that's what seems to be going on in that line of code. That is, you sample from the base distribution after taking the log of f theta of xi, right?
Yeah.
Because that is what would be probability Z, the probability distribution over Z of f theta of xi, if I understand it correctly.
So I think it's just that maybe this diagram is confusing because x goes directly to here, and then it goes backwards, or it goes somewhere else because x is not going through whole, and you get Z at the end. X goes directly here. That's the first step you do is.
Yeah, but that, because this is a very simple thing, and maybe as we go to more complex examples, then we'll see X go through a network to create the F theta. But in this case, it's just directly going as a mixture of samples, and we also have the base probability distribution, which is, either uniform normal or the beta distribution.
So yeah, that's why it's confusing. It's saying, and then Z has its own distribution,
which is the uniform normal,
which is the uniform, right? In
right.
this case,
so that's why if you go back to the code, then at least that explanation seems to fit the code, right? Because you take the log probability of Z, which, as you pointed out, is you get the Z part from there, and you take the log without the log. So you take the log probability of Z because you have not yet taken the log, and then you pass that in and take samples from your base distribution corresponding to that, which is because you need to do the PZ of the f theta of xi.
Okay.
The thing that they seem to have done, which, like if you go back to the slide, is move the log in and taken the probability of that, whereas as written in the equation, it seems to say log of the probability samples of that. You see what if you go to the slide where we were looking at the two parts of the equation.
Yep, this one. Okay.
Yeah, right. So the thing that, and again, as some of these things, the math and so the notation here seems to say take the log of the probability distribution of Z of the values of Z, right? Whereas at least in the code, as I understand it, and anybody else following along, feel free to correct or comment. What we seem to have done is take the log of f theta of xi and then take the pz of that.
Mm-hmm.
Right, according to the code. Now, I'm not, I have to think through whether they are equivalent, but at least that's what we seem to have done in the code. Is this guy we calculated, which is what is Z, as you pointed out. Then we take the log probability of Z and then take the probability of Z of that value.
Okay, so yeah, I think from the explanation, maybe I'll go over it again, and then what I think is going on, and maybe you can see if I'm right or not. So what actually is going on is that X goes into Z first. So this this should be this block here, and assuming we just have two. Let's ignore these two. I don't think I can edit it, but yeah. So this one belongs to this, and then its output, and this is our uniform. This is our uniform, but the idea is that the distribution, the small slice of distribution, are the same. So even if you look at it, this small slice here and this small slice here, they're the same. So getting the log, like the log probability of this one is equal to getting the log probability here. So we can still use that formula, this formula saying base dist log probability plus log determinant is the same slice here, but in this distribution. So I think it would have been clearer if it's saying X goes into F theta and produces Z, and then it goes into uniform, but then Z comes from PZ of Z. Or I don't know which one is PZ.
Z comes, no, you're exactly right. Z comes from PZ of Z. And so, the only change that I was commenting on is instead of it being just Z, it seems to be log of Z.
Okay. Oh, but that's just for
code.
this equation. Yeah, this is just because you can
if you look at the right hand side, that's what I was commenting on, that the difference is if f theta xi is Zi, then I would have expected the log to be after the sample, but as coded, it seems to be you take the log of Z and then sample from your Z, sample from the distribution of Z, which in our case is the base distribution. So the log seems to have gone inside.
Yeah.
And I guess they're equivalent, otherwise it wouldn't make sense, but that's something I have to wrap my head around. But that's what, at least as coded, seems to be the case.
Okay, yeah, so I think that what was confusing was I think this is the mixture of Gaussians, this is the uniform.
So I guess they're using the uniform to basically perform maximum likelihood estimation, aren't they? And that's the way that they're getting the negative log likelihood. So I think for them to actually get a loss, that's why they're sampling from the uniform. Does that make sense?
Is that
so if you look just below that, so
this one,
negative log likelihood, so just below that.
in the code?
Yeah, yeah. So basically where your cursor is now, just underneath.
Oh, okay. Oh,
So
okay, I see.
So that's where they're to perform MLE and therefore to optimize the model. I think that's why they sample from the uniform, isn't it? On each time.
Oh, and then why is there a mean here? Does that mean?
Because it's maximum likelihood estimation.
Oh, okay. Yeah, it's the you have to turn it into a single number, right?
Yeah,
Expectation.
that's
Okay.
it. Yeah. So I think that's sort of where the uniform distribution is coming into play. Although I'm still trying to understand it myself as well. But I think for the purposes of sampling and getting that loss value.
So if we were just doing one layer and we didn't care about the the space distribution, I would just say I'll not worry about the determinant, and Z is going to be yeah, Z is going to be the weights, and I could take the log of it, right? So, but since we're pushing it through one more, we add the determinant to it, and then the negative of it is here. So the loss, so the log probability acts as two different things, to get the density and also to get the negative log likelihood, which sort of makes sense.
Yeah, I guess it'll be helpful to look at how it changes when there's more than one flow layer.
Okay, I don't. This is the only one that I was looking at.
Yeah, I've not looked at the others either, so I'll have to probably look ahead and see. But
okay, mixture CDF. I'll see if I can.
Yeah,
So
let's
this,
finish this and then maybe we'll plot through the next one to see whether some of our explanations hold under as we move forward.
yeah, one of the weird things that I found. If I don't know if this makes sense, but so if I actually run it, the base distribution log probability uniform of Z is always 0. Z1 always seems to be 0, so I don't know why that is. No matter what I do, Z1 is always 0. I don't know if I need to iterate it enough times, but don't know if that makes any sense. Maybe it's just training time before.
Right. It's almost like when you initialize your weight matrix with zeros coming from a different direction altogether, it never changes, right? Because you're trying to multiply 0 by a gradient. That's also 0.
The uniform doesn't do anything. It's I guess it's just the gradient is getting passed along then. I mean, so because is the log probability of a uniform always 0?
But Z is not Z that you're passing in is not uniform, right? Z that you're passing in is a val it comes from the flow.
Yeah,
so
Z
determined
is
by X.
Yeah, so it is just a mixture.
So it comes from the mixture of the distribution. Yeah, and the X repeat is just for the number of dimensions that X has, correct?
Which one, the dim?
Or is it? No, X repeat.
Oh, it's because there are n components. So there are 5 mixture of Gaussians. So you have to.
Correct. So it's just that you will find for each of the 5 dimensions or each of the 5 mixtures that you sample from.
Yep.
Correct?
Yep. And then you.
So then what I'm saying is, and you multiply by the weights.
Yep. And then, yeah, it's just doing the mixture of Gaussian computation. it's taking X and doing the Gaussian here.
Correct. So Z, right. So Z is not, so since Z is the output of that, Z is not uniform normal, right? So log probability of Z, where Z comes from a mixture of distribution, times the weights, and then the weights initialized to 0, or are the weights initialized randomly?
Oh, uniform has no weights, I believe.
No,
Well,
no, no.
it
But
is
I'm saying
0 to 1.
my point is, yeah. But my point is the Z is not coming from.
Yeah, Z comes from mixture of
value.
Gaussians.
Right. So Z comes with a set of values that are non-zero, right?
Yeah. But when we take the uniform log probability of Z, it always seems to give 0. And I don't know if this is actually makes sense or it's just some initialization time. I did like step over quite a bit of these. I can go into more epochs, I guess, train epochs. So
Regardless, your code seems to be working though, right? I mean,
yep, it works. So I don't know what's I'm not sure what is going on. I can do the beta and then see if it changes. The other one is the beta, right? So the part 2 is the beta 5.5 beta distribution, which is, I guess, so I didn't know what beta distribution was, but it's sort of like Gaussian, I think, but it's like slightly tilted or right, something like that.
it's for, I think it's for smaller distribution. Like Gaussian is like, theoretically infinite. Beta is, I think, for smaller data sets, if I remember correctly. I may be wrong.
Okay,
Yeah, I remember it's used a lot in sort of Bayesian modeling, and
Yes.
it sort of allows you to put more prior knowledge into like the initial distribution. If you think it's skewed to one event over another, it sort of allows you to adapt for that. And I think, I know that one of the best priors you can use is uniform, but I think beta is also one of the best as well, although I'm not that knowledgeable in that area. It's just what I've sort of read.
I watched, I read a few articles, watched some videos, and then I really wasn't sure what's going on. Everybody seems to have different ideas. The only thing is that you can kind of get lopsided here. But anyway, but it's not uniform. It just has a different shape, I guess, depending on.
It seems to be a controllable thing based on your values of alpha and beta.
Yeah, I think Ben's point is
generate a variety of codes.
Right.
Sorry, go ahead.
No, I was saying that Ben's description, I think, is closest. Based on your priors, your distribution can change, and that's what you pass in.
Okay. Yeah. Yeah, there seems to be a lot of theory behind all of this. So but anyway, I can try and do that. I didn't make this one here, but we just see if that is non-zero. Oh my gosh. Okay, what did I do wrong? Python. Sorry. Okay, Shift F6. And I'll just copy this over so that it has the beta part going. So this is the beta distribution, and it should be the same. And Z1 is here, and then I can just make the. Yeah, and Z1 is
Got
not.
numbers in it. Yeah.
Yeah, it's slightly different, but yeah, now it's like this one is 0.4. Okay, but
Small
I think
values, but non-zero, right?
Yeah, non-zero. So if we look at the results, so I think it seems to be similar. So this is the original, this is the sampled one, and then yeah, I got too many of these
With
open.
a beta distribution, does it give a better match? Is the loss lower? Or the whatever the metric, like I forget.
Okay, let me run it
we
again.
use to compare the two models.
This is the one, 1D flow. Oh. Okay, so seems to be about the same. Oh, so this is for the uniform. I think the loss is the bits per dim, or yeah, I think so. And this loss is slightly different.
It's steeper.
Yeah, it's steeper. It converges much faster.
Right.
The beta or the uniform?
This is, yeah, the beta is converges within 8 epochs. But obviously the beta also does more computations to calculate the distribution. Yeah, that's all I actually looked at was just the first version, because I still have to figure out what's going on. So in homework 2, where is homework 2? Okay, for homework 2, if I can get through here. Okay. The first problem is 2D, so this one. So in order to start doing it, you kind of have to, and it's still autoregressive, so it's similar to the old one. But I actually haven't looked at it all that much. So I just wanted to make sure I understood the 1D version first, but then I was completely confused about which way the flow is going and which way what is going.
But I understood all that. I mean, flow is just a term used to indicate the mapping to something that is invertible. I mean, it's just same as autoregressive with constraints, new constraints of the determinant being computable, not intractable, and having a function that can be used to map to Z, which is invertible. Correct? I mean, that doesn't, even though and you know, those two rules in addition to everything else kind of ensures that we have what is called normalizing flows.
Yep,
it's oversimplifying, but I thought that's kind of the takeaway summary of the. Am I wrong, or is that?
No, I agree. I think I'm just confused because they put it down here. Maybe it would be more intuitive to say X goes into F, not F theta of X. And here's your first one, and here's your second one, and so on until the last one is not dependent on X. You know, I guess it is dependent on X, but it has gone through all of these. So you have X turns into Z here. So we put in X, you get Z out. Or some, I don't know if Z is here or here. Z is here, right? And then, but P of Z is, so this would be F, but P of Z would be, no, it can't be. So this, again, this one doesn't make any sense. So P of Z is distribution of Z, but here Z is F theta of X. So is F theta P of Z, but that's not the case because P of Z would be uniform, which is here. Or
No,
all the directions.
Okay.
Okay.
The way I understand this notation, in fact, is, or when I say this, I mean the notation where it says Z and then this curve sign is at least, I mean, I just learned it last week or 2 weeks back, that it's more that Z sampled from the probability distribution of Z. And the Z itself is generated through this from X. So that's what we see in the equations, right? Because your Z is generated through the mixture of Gaussians of X, and then you take the and in order to get this probability distribution, you sample from the probability distribution, which is a prior that either a beta or a uniform.
Okay.
And the values that you use for Z to sample from the known probability distribution of your latent are coming from the mixture of Gaussians in this case.
Yep. So this block, this one that I highlighted, is PZ, and so if Z would come from here, yeah, I'm still not.
Because that's what the code is doing, right? Because the code is doing that, it's computing Z as a mixture of Gaussians of X,
Yep.
and then using those Z values to sample from the prior known distribution of either a uniform or a beta.
Okay.
So
yeah,
PZ is a known probability distribution of either a uniform or a beta, and you use the Z values to sample from that based on your X that you get.
Okay, so that makes sense. So
right now, what about the next? Can we even just spend a few minutes to see whether we can make sense, assuming that our understanding of this problem is correct, whether the second problem, even the solution, and we can just look at it.
Oh, I haven't looked at it, but we can still go here. Composing flows improves expressivity. Yeah, I actually haven't looked at it. Different alphas. Yeah, this would be interesting. How do we compose
if we
all
can
of this?
just even, if we just look at that, what he, the paragraph that he had at the top,
Okay.
like what it's saying.
Yeah, it's
Okay, so let me. Sorry, go ahead, Mark.
Oh yeah, I'm not sure. Yeah, do we want to continue on this next week, or do you want to just kind of try and figure it out with here?
My vote would be, let's at least go as far as we can, and
Okay.
if we get irrevocably stuck, then we at least know what problem that we are stuck on, and we can all think about what could be explanations, right? I mean, that way at least we narrow it down to where we are stuck collectively or what we don't get.
Okay. Yeah, and I think this here in this one, it's just plot. This is the logit, just a curve, right?
Yeah. So at least from the paragraph, here is what I got out of it, and I wanted people to comment on whether that understanding makes sense or not. So if you go back just a little bit, so we can stare at that paragraph. Yeah. So there, what it seems to be saying is, in the first example, we just used a single CDF, right, to map from the sample and the combination of we were trying to arrive at the combination of the logistics, but using a single CDF to map from a uniform or a beta. And if this seems to say that becomes hard to do, therefore in the general case, and this is where the multiple of layers that he has shown in the picture comes into play, which is the composition of the flow. So what we saw in the first example is, think of it as a single layer flow, as Sujit was also commenting on. And now we begin to build the flows as like a neural network, which is a composition of flows. So each stage is itself a flow. And then you compose the flows one after the other in order to map a more complex, like 10 mixture of Gaussians. And that's what he's now beginning to try to do. Or at least that's what I take away from what this paragraph seems to say. Does that make sense, or am I off?
Yep.
Somewhere else?
No, it makes sense.
Right. So that corresponds to trying to explain your confusion. You should ignore the multitude of things that is shown, because in the first example, he was just using a single step to go from X to Z. Whereas now we'll begin to go through multiple steps, but each of the steps will be an invertible flow model. That is, you can go from X to Z, and you should be able to go from Z to X. Again, go and each of those steps will go from X to Z, Z to X. But Z could be, whatever you can name it as, without confusing Z1s, which are the components. You can, I don't know, call it ZA, ZB, ZC, and so on. But each of the ZA, ZB, ZCs would still need to be invertible flows. That's when you can compose them.
Okay, yeah, and I think they want to use the logic transform for it. It's a different curve, right?
Yeah, and maybe because that is invertible and so on and so forth. And its determinant can be whatever determined easily, because we need those properties, right?
Yeah, it's logic transforms with different alphas. And I think they want to use this as the CDF. Okay, so this would be the composition. Flows. Okay, you have to give a list of flows.
So that would be like the number of layers. If you think of it as layers in a network, each flow is a single layer, is a layer in a neural network, right?
Yep.
Because
Yep.
each flow is itself invertible, and you compose them, which is you add them along, stack them.
So it's basically the same code as before. You do flow, you take the Z, and then you get another Z out, and then the determinant, and then you add the determinant, and then you put the Z back in, and then get the next determinant, and then add the determinant, just from the equation, right? So
Yeah.
where's
Yep.
that one gone? This
Yeah.
where is that the one? I is there? No, that's data point. Sorry, somewhere here.
It's this, right? Because it's the layer stacking. So it's kind of like the picture of the layers stacked, which is those boxes that we were staring at.
Yeah. So it's still yeah. So it's still yeah. So it would be so you'd go from X to Z1, Z2, Z3, Z4.
Yep, and eventually the Z you get, use that to find the PZ of Z, which is the first part of this guy, self.flows, the last one, base distribution and log probability, and then you get the log determinant the way you, because you, like you mentioned, you kind of recursively compute the or not recursively, but iteratively compute the next log determinant from the prior, and you keep adding to the log determinant, and then you get the final log determinant.
Yep. And the log probability is the same. They still have a base distribution, and then you
right.
Yeah, you get,
And it's the self.flows and the last, because obviously what you get out of the composition of flows finally is your last Z. So that's why it's the self.flows -1, because it's the last layer of the composition of layers of your module list.
oh, okay.
And the flow of that is what you take, and the output of that Z is your what you pass in to this self.flows.-1 base distribution.
And
I couldn't have coded this in a million years, but at least we can try and figure out what the code is doing.
yeah, I don't know if each of these base distributions are different, but I think they would be all the same. But
yeah, can we look at the base in this case? Is it just I think the base just remains the same, right? I don't know that there is. It's in this case. Is it? Sorry, is it just the uniform or?
Here, load flow demo 1 training. I guess it's in here somewhere. Load flow demo 1. Oh no, here composition of flows. Here we go. Mixture CDF flow number of yeah, it's all the same. So use wait I think mixture CDF flow, and then it goes into logic transform and goes into mixture CDF flow, and then logic transform and mixture CDF flow. Does there need to be some sort of do they have to do this every time?
So what is the mixture CDF do? The logic
same,
transform is the non-linearity, right?
yeah, it's the same one as
yes.
before. Mixture CDF
it's a single step flow.
No, it's this one, the mixture of Gaussians.
Okay.
So the base distribution is always uniform, I guess, because they don't specify.
Okay. Yeah. But also this just seems to be saying exactly like he described, that you can think of the logic transform as just a nonlinearity applied to the basic conversion of X to Z, which is what is the mixture of flows doing, right? So that combination, you can think of taking X through, like, I don't know, a convolutional layer or a linear layer, and then applying a ReLU like nonlinearity. So that combination of first two steps you repeat in order to compose a flow.
Okay.
So composing a flow seems to be like a mixture of Gaussians followed by a nonlinearity equivalent, which is this logic transform. And again, you repeat the same thing. So this is like a 2-layer, or I don't know whether it's a 3 because of the last mixture, but 2 or 3 layer composition.
Yeah. So yeah, I don't know if these two, maybe these two form a layer, and then the last one has the uniform as a layer. Because we use the uniform.
Last layer, I mean, it's almost like what we do in a typical thing, right? You don't necessarily take the ReLU after the last one. You don't apply the nonlinearity. You just output the legits.
Well, I think the difference here is that I'm scrolling. Sorry. In this one, so the base distribution is only used for the last one, right? For the other ones, the base distribution is never used. But we just flow it through the. We just go. So this one goes from.
Yeah, the z just gets nonlineared and then goes to the next as x, is what you're saying, without going through the without going through the base distribution, right?
Yeah.
Because you're not mapping it yet to the CDF or, right? Or you do that only, you don't do the PZ of z until you get to the final z, which is the output of all of your compositions.
Yeah. So there's something. Okay. Yeah, and then it shows it works, and
is that better? Or I guess it used to model something.
I think it's even faster.
It doesn't get better.
It is faster.
But it says it doesn't get better.
It is faster. So it was about 15, but with this one, it's like 8 or 9, and it's now about less than 5. So
actually the paragraph below says that.
Oh, okay.
So it's less overfit, right? And if you see the test loss, it's much lower than,
Oh, okay.
Yeah.
That's a good point. So
actually, what is interesting is that training loss remains high, but the test loss is lower.
Yeah, it should be the opposite, right? The test loss should be higher than training loss.
Right.
It's kind of interesting.
Yeah. Anyway, I think this one is fine. It just has the weirdness.
But also,
so go ahead. Sorry.
Sorry, the second or whatever, that last line is interesting because he says that, when you change the number of layers, that means that, this combination of flows and nonlinearity. But then the other comment, which is also interesting, at least it gives us a way to think about it, is the number of elements in each layer is the number of mixture elements in each CDF, which is, and he says, which is akin to the width of the deep neural network. That is, like how wide it is.
Okay.
It's equivalent to thinking of, if you increase the number of mixture elements in each of them, that's like increasing your width. But if you increase the number of compositions, that's like increasing your depth.
Okay.
That's what this seems to say.
Yeah. So
right? And that's kind of what he's. Sorry, go ahead.
Yeah, he is counting the logic. What was that called? Logic transform and mixture as one layer. So this forms one layer instead of 2 layers. They go together.
Yeah, that would be right, because it's like the linear followed by ReLU. That's the analogy at least I use in my head. Right? You have the linear, like you multiply x times weights or whatever using a linear layer, and then you take the ReLU. So that's equivalent to taking a mixture of flows, the number of components, and then logic transform. And he says that if you vary the number of components here, instead of 5, make them 10. That's like akin to increasing the width of your network, of width of equivalent neural network, for example.
Okay. And so let's just go. This one is, what are they doing? Calculate sweep losses. I don't know what that means, but
I think he's just showing how it varies when you increase. For the two explanations he gave, right? One is increasing the depth, and the other would be increasing your number of Gaussian mixture components, and that's analogous to increasing your width of the network. So
Okay.
that's what he has plotted, right? Number of components per layer, and then the number of layers along the y-axis, and the number of components per layer, meaning the number of Gaussian mixtures along the x-axis.
Okay. Yeah, he's sweeping the parameters, the number of layers and the number of components, right? So, okay.
Right. And then just now, the interesting thing is best possible NAS per dim once we have two Gaussians in a single layer. I can't see the values in
All of them says 1.28, I think.
the, yeah. And the lowest seems to be two Gaussians.
I think the higher it is better. They're all the same number, but I don't know. When we have two Gaussians in a single layer, so number of layers is this, number of Gaussian, number of components is this. So I don't
So
know
it
which
seems
one
like
is.
lower the better, right?
Two Gaussians in a single layer, so it should be this one, but I don't know why it's.
Right. No, that is, so the lower is better for NAS per dim, if I recall.
Okay.
Can somebody
Okay.
confirm?
Yeah, it looks like that.
Yeah, I think so. As you increase the number of components or the layer depth, it gets progressively better.
Yeah, it flattens out is what he's saying. But beyond 0.99, it doesn't get any better because you've already captured
Yeah.
what you intended to.
Okay, and then what is he doing here? Training uniform. Oh, I think the data is uniform here.
Okay. X is not a mixture of Gaussians, but it's a uniform. Okay.
Yeah, uniform, and then
Mm.
kind of becomes like this.
Yeah. Interesting.
And yeah,
Getting
the
there.
same, and the same sweep, and then it
Oh,
says
and the same sweep. Yeah. Here it's interesting, right? Because it's 3, no?
yeah, the more you increase the number of components,
And the number of layers. Look at that.
yeah, it just keeps
That's when
getting better.
because it's right. It's almost like, trying to model a complete uniform is like you really need very large number of layers and a large number of components per layer.
Okay, and then complicated distribution. Yeah, similar here with mixture of Gaussians. And
Mm.
yeah, similar.
Yeah, this also seems to say we need to go, although I would say probably at about 5 layers and 3 layers, 5 components, it kind of gets to a fairly low point, 1.38. Nothing is lower than that, right? But you can get there multiple ways, it looks like. You can get there from 4 components and 4 layers, or 5 components and 3 layers.
Yeah, for the 138, right? So this.
Yeah. So it seems like, if you went 6, I don't know whether you can come down to 2. There's some kind of an arc going through there. Now, is the input generated through a mixture of Gaussians in this case, the complex distribution, they say?
Yeah, I just have to look at this one. Don't know if I can find it here.
Doesn't look like it, but.
Um, Okay, so distribution is complex. Okay, complex x tan h of sine of something.
No, so it's a way. It is complex, not a combination of Gaussians.
Yeah.
Tan h of sine of something power. Okay.
Yeah, this part is
Very
just, I think, same.
generating. Yeah. But it's more the whys, how they get it from the x's, and that's very complex. It's not just a combination of
Yep.
Gaussians. Okay.
Okay, and so yeah, and so I think this is the 1D part. I think it's yeah, it uses the same mechanism. Yep, and so we have 2D with autoregressive flows. Just look at so the flow seems to be similar, and they also have the base and the mixture and the number of components. So,
Yeah,
but
there
it's
seems to be here one additional complexity of the conditionality of, right?
yep. I don't see where it's added here.
Yeah, right in the
Maybe it's here, autoregressive flow here. Okay. Dim flow conditional equals, yeah, conditionality. And so flow conditionality conditioned. Where does it go? Oh, sorry. I'm not used to this, sorry. I'm scrolling. Yeah, we were here. Yeah, this conditionality. I don't know where it's being used here. Oh, here, MLP conditioned on something. So in which if we go up, we will be here on this condition. Forward MLP dot conditional. Self dot MLP. MLP is MLP. It doesn't have a function called MLP.
this capital MLP seems to be a class, right?
Yep, it's right here.
Into which is passed conditional dimension. Yeah, this one seems to be, you'll have to work through what's going on.
Yeah, yeah. I think I have to set up the code to look into it. This might be from an end module. That it just goes to the forward. Oh yeah, it just goes to the forward. Sorry, never. But I don't know what the conditional does. So conditional is probably it's probably going through the layers of the MLP. And MLP is conditional dimension and layers hidden states and components times 3. So the conditional dimension is, so condition is torch.chunk, log scale with logits. Yep, depending on the conditional, I think it produces different weights, weight logits, and then that is used to get the weights, and that weights is used here. Also gets a lock. LOC is like their code for the mean of the mean of each Gaussian.
Yeah, what is, sorry, if you go back up, what is the lock returned as from the MLP?
The, log, scale, and weight logits.
Right, but that's chunk of the MLP conditional 3dim1.
So I think
I
you
wonder
have to
what
look
the-
at output size of the MLP.
Hmm. Then
And
chunk
that should
seems
be
to get
3.
3.
So it's n components times 3. So number of Gaussians times your mean, log standard deviation, and then the weight. And n components is a number of Gaussians. Yeah, I think in the homework it said like if you wanted to do autoregressive, you could use flow for each dimension, and you could use the same neural network, or you can use 2 different neural networks, 2 different flows. So maybe you have flows for the X part, and then once you get the X, then you have the X1, sorry, and then X2 would be a different model, or you could make it the same model, but then you'd have to do you'd have to add a conditional saying, well, when it's this model, you have to have a slightly different set of Gaussians. So I think that's what this MLP does, is to learn that if you're using it as a single one, yeah, if you're using it for X1 or you're using for X2, and I believe we're using the same one for X1 and X2. Sorry, I'm scrolling. Okay.
Oh, I see. So each of the X1, X2, Xn now will be passed through independent flows with X2 conditional on X1 and
yeah,
X3 on X2 and so on.
yeah, it's only 2 dimensions, so just have X1, X2, but yeah.
Yeah, in this case too. But in the general case, that would be true, right? It would just kind of condition on each of the previous X's.
Yeah, you would say like which variable are you? You know, I would say I'm X1 or X1, X2. You know, and that condition would give you the second dimension. Or the other option is just to have a completely different neural network for X1 and for the second X2 part, or combine them.
Okay. So you're saying, so if I understand you right, you're saying depending on the condition, you can change the network, or you can just use the same network, but for the variety of X values, in this case, X1 and X2, because we limit it to 2 dimensions.
Yep.
Okay.
Yep.
I see.
I think that from all the autoregressive stuff, that's how it was, that we just use the same neural network. And
yeah, but I was just thinking through mapping that into the flows. So you would have, like in a single dimension, we just had the flows. So you would use that as a network for your X1, but for your X2, you would then condition a similar network or a different network.
Yep.
And pass it through to do the same thing.
Yeah, but it would give you 3. Second network would have a slightly different Gaussian, like this is the mean, sigma, and the weight would be different, because then the MLP condition would change it up slightly for them. But yeah, I don't know what condition is, but it seems to be the conditional dimension. Conditional dimension is 1. It says, okay, in layers, hidden size, and components. Okay. Seems like it's only sending 1, like saying with which layer are you? No, not layer. Which dimension are you? Are you at x1 or x2? Because the input seems to be 1 here, the default one. Because I was thinking that it would also add the actual value that it encountered, but it only seems to be doing the dimension. Yeah. Because depending on what value you encountered, your distribution would be different, right? So if your x1 says I got 1, then I think this means that they're independent or something like that. Yes, yeah, okay. So I'll just scroll down
and in
here.
this case, they mentioned it, and if somebody can kind of expand, or I didn't exactly get it even when we said it, but in this case, it seems to be that when you go back, like for example in the invert, then you mentioned it in the class and I didn't get it then either. So it's, if anybody has the understanding already, otherwise and poke into it more. But here it says, right, like the X set to be searched through a bisection search. Is that because we have 2 dimensions, or why do we have, or what's the reason for this bisection search?
There's an invert in the regular one also. The 1-dimension one also has it. It's, I don't know if
What
it's,
do we do there, for example?
find the exact X5 bisection. It says the same thing. I don't know if it's ever used, so I'll try. Let me see if I can, if it's ever called. It's never called, so I don't know what it does. I mean, we're only calculating the density right here. So I think you'd call the invert to say, I have some value of z. What is the x that it should be from, right?
Also, would you do that when you provide a z in the latent space and want to see an output in x?
Yeah,
I think that.
I think it's the next, like it's the next chapter with the latent space. Then that's when it would be useful. Right now, I think all of this is just like what's x, what's the probability
Going from
of
x to z.
Yeah.
Yeah.
But
so
if
going from x to z, but yeah. Sorry, go ahead.
Yeah, and so, but what if we want to, if we have z, but I don't know how we can get z because we only have x. So only if we manipulated things in z. Yeah.
Yeah, but it's more like the example he shows towards the end of, if you want to manipulate, if your z, which are the latent variables, could be like your, in a case of a face, beard, smile, eyes, color, hair color. And so if you want to sweep the z's and make somebody have a beard, then you could move the appropriate zn, and that would go from a clean face to a bearded face, for example.
Yeah.
And in that case, you'll need to go back to an X, right, from a Z.
Yeah. So I think in that case,
But
go ahead. Sorry. Yeah.
You would use this. But what I guess I'm missing, and that was more my precise question, I guess, is, why a bisection search?
Oh, this one. Isn't that how you search a distribution? I think this comes from the SciPy. So find the root of a function within an interval using a bisection search. Oh, okay. It's oh, sorry. So you have f and you have a and b, and you find a 0 between those 2 points.
So it's akin to going back to a distribution, or sorry, no, find the root of a so finding the function from.
So we have f, and it says from -20 to 20 find when it's 0. So f of x is defined as the flow of 0, 0. Yeah, x minus c l. Okay.
So given the flow, find because f is the flow, right? F of x is the self dot flow of the value.
Yeah. So it just
minus the mean, I guess.
Yeah, it just goes through the flow and then tries different values of x, and then until, and I think this does use the gradient until it finds the place where it's 0. Or not the gradient, sorry. So you test left and you test the right part, and you say, well, one is positive, one is negative, so there must be a 0 in the middle somewhere, right? So you just kind of move them around and see how fast they. Yeah, so I think there's a method. It's a numerical analysis method, like bisection.
Okay, yeah, no, that's
search.
fine. At least that then I can figure out the details. But it helps us go from z to x using trying to find a value.
So we have z here and we have x here. So if we know how to get, so we can try this x and then say it's positive, try this x, it's negative. And then you say, well, let's move this over here and let's move this over here. And then you kind of try this and then you try this. And then depending on the gradient, you'll say, okay, how much to move until you hit the 0. So that's just a search from flow, because we have flow that will take us from x to z, but we have z and we want to find x. So we have the bisection search to do it.
Okay, got it. Okay, thanks. That helped.
I think there's a gradient. Oh yeah, do you need the gradient? I don't think you need the gradient. You just calculate the midpoint of a and b, and then you just kind of search, I think. If you even forgot, yeah. Yeah, just take the midpoint of it.
It's like Newton's method or something. This way back I learned in numerical analysis. So.
Yeah. Yeah.
Okay, that's why you need. Okay, now I got what the context, the details. Yeah, I can look it up, but I at least understand the purpose and what we are doing there, how the math of it can be, looked into. Okay, thanks. That helps. That's why you do a bisection search to go back from z to x. And like you said, it's not used now. It will be used when we want the to sample, right? No, to go back and generate. It's more for a generation of x.
Yeah, to kind of play around in the latent space, probably too.
Right, and generate samples.
Like what they say, if you get all the ones that are smiling, and then you take the average of all the ones that are not smiling, and then you subtract the z values, and you get the vector that says, okay, this will change smiling to non-smiling, and then you can add, and then you can find the x that gives you that value. Like, yeah.
Cool.
Maybe that's why.
Good. So we made pretty good progress because we went through most of this second thing too, I think, right?
Yeah, I think the base idea of how we can flow it, if that is clear, then I think all of these are just like additional stuff on top of it, right?
But that's why the first one-dimensional single input thing was important to grasp, and at least so far our understanding seems to hold, right?
Yeah.
Of how things happen.
Yeah, it's still using one dimension, right? So the mixture dist, and then you're still doing the CDF, and then.
Oh yeah.
So Yeah, so the same idea happens over and over. But yeah, I kind of was confused. Yeah, probably have to think about it a little bit more, and maybe it's then it can sort of click what the diagram is meaning and what the notation, all of them mean. Okay, so do you want to continue on, or
let's see, so is this just an example of trying to do it then we can wrap this up, and then the training in 2 moons, if it's just a matter of an example, then we can probably go through that and stop.
okay. Yeah, seems to be just an example. So yeah, I think as we're talking about what is the SVM, right? This is one of the famous examples of SVM, where you can
right,
make a layer that classifies these two by like making a boundary between these two. Yeah, and so I think it's still 2D, but they probably have the same thing where you give the your training data set is a huge vector of X and Y's.
Yeah.
Okay, and then data set moons. Okay, I'll just scroll through. Yeah, I don't know how you printed the latent space, but
Wow.
So,
and especially the plot of densities is fascinating, right? Because it begins to place the densities where it really matters, and then slowly gets to the moon from a blob that's just at the center, right? If you go back up at epoch 0, what's the density like? It's all in the middle, I would. Well, it's actually not.
It's probably Gaussian over here and Gaussian over there. All of them in 0, 1, or no, I guess not. 0, 1, no.
Yeah, it's like 2 blobs, and then slowly it splits, it separates the blob and spreads them out.
Yeah, it's interesting to see how they plot the latent space. It's probably the mean, or it's some value Z. So I don't know.
Fascinating.
And I think there's another one, the face one. So this is the 3 different classes. Is it 3? Okay, it's 3 different classes. Yeah, the latent space is already pretty good. Oh, second one got worse. Okay, yeah. It created this distribution. I think the latent space wants to fill up everything. Yeah.
Yeah, that's the other thing I noticed, right? Like the yellows go all the way up.
So interesting to know how the latent space is. Yeah, parameter sharing. I think the other one didn't have parameter sharing. I'm not sure because the condition was only on the dimension and not on the on what actual data was there. Could be. But yeah, we can wrap up here. And yeah.
Start here for the next.
Yeah. So for next week, yeah, if someone else can do it, that'd be great. I can still do it if there's no volunteers, but if nobody wants to do it,
Thanks for.
Yeah, but please somebody else do it. So yeah, you can post it,
even
or
just a discussion. If somebody else volunteers, if not, you can just take us through like we did, and we can just collectively try to find explanations or go through it. Don't
Okay.
have to do a lot of preparation as much as just setting it up in the code like PyCharm, and then we can at least just look at it as we go along.
Okay. Yeah. Can go a little bit faster. Oh, sorry. What was it? I was trying to find the homework. Yeah, this is the homework one. Yep. And so this the smiley face is the first one. That homework 2 is and there's some more. I think it's the autoregressive flow for images, and
This is an actual MVP. We haven't gone through it, but I think the other thing is, hopefully Jonathan feels better by next week, so he might use the first part to kind of go over the theory, and then we can use the rest of the time to go over what is remaining in the collab or homework.
Okay, and those are the things. Yeah, those are the three things. There's a bonus question. Okay, multi-scale, glow. Yeah, if want to look at it,
but as you said, once we understand again probably the basic of how to do it when you are sharing parameters, then other ideas can just be layered on top.
Yeah, it's that was confusing. Is that I think I'll still have to go through and like really what symbol means what, and how what are these boxes, how is everything set up, how kind of just
right. Yeah.
get
No,
clarity
I mean it's not, because here he's showing it, I think, for the most general case, whereas we started with the most rudimentary case or the base case, which is just almost like a single layer. You go from X and then you get a distribution. So there's none of these multiple. And then you get to the multiple of these boxes only when you begin to compose flow after flow.
Yeah, that's
and
probably
when you don't, then you just go directly from X. The output of the next box is your F data of X, and then you just sample using the PZ. The PZ is uniform or beta, and you get the Z from your F data of X, shove it in there, find the probability, and off you go. So it's just a one-step thing for a simple case. But then it begins to show, how do you compose? Well, each of these should now need to be a invertible and determinant, easily determined layer, and then you can add this ReLU-like activation by whatever the legit function and stuff. So that those two things, the mixture of Gaussians and the ReLU equivalent logistic function, go into this box, and then you put multitude of these boxes, and then eventually comes Z, which is where you take. That's why you do the self-dot-base distribution only on the last layer's output.
Yeah. So so another that's thinking maybe this Z is like a maybe this is Z1, Z2, Zn, and then Z is like everything mixed together, or so Z is
it is
Zn minus 1 composed with Zn. It's like that, or there's Z's here, and so there's like a little bit not so clear. But Jonathan posted some papers that are also maybe different, more elaboration, and we have the code to also look at it and play around with. So that should be interesting. But I just started looking at it yesterday, and I couldn't figure out what's going on.
No, I think it was good, great, and no issues. I think, in fact, as long as we you can pull it up in the PyCharm and be able to run it and look at it, I think we can collectively figure it out like we did right now. So that's fine. I mean, we're here to kind of try to help each other understand anyway. So doesn't mean you have to figure it all out before.
Okay. I'll move most of these to PyCharm and kind of get it running. So if we don't have anyone, then I can do it next time, or if someone else, then please.
Yeah, that'd be great. Yeah. If anybody volunteers, that'd be great. But if not, we can just collectively go through it and
Okay.
pull it up. Thanks, Mojan. That was helpful and insightful.
Okay.
Okay. Anybody else have any comments? If not, thanks for joining, and we'll see you all next week.
Thanks, Martin. Right.
Yeah, thanks a lot. Cheers.
Yep.